All right, so here's segment 3 of chapter 6. So we were talking about heat capacities, and next we're going to look at is specific heat. So specific heat is the amount of heat energy needed to raise the temperature of 1 gram of substance by 1 degree C. So basically what we're going to do is take that capacity and look at how it can break down into specific heat and mass. So we said there was a couple of dependencies for capacity. And so capacity then is equal to specific heat times mass, or we can think of specific heat being the capacity divided by the mass. Now this makes it an intensive property, right? Because we have two extensive properties, but because it's a ratio and proportion sort of idea, much like we saw with density, that means we're going to have an intensive property. Okay, so the units here will be joules over gram degree C. Or you can do calories over gram degree C. So if you Google this, you'll see typically both of those units are available. Now this is unique to each substance. So water is going to have its own specific heat. Insulation will have a specific heat. Metals will have specific heats. The large specific heat simply means that the substance releases large amounts of heat as it cools, right? So it basically says if you have a large specific heat, then large amounts of energy can transfer. All right, so calculate the specific heat of water if the heat capacity of 100 grams of water is 418 joules per degree C. So of course, specific heat then is capacity over mass. So we'd simply plug that in, 418 joules per degree C over 100 grams would give us 4.18 joules per gram degree C. All right, so what is the specific heat of water if the heat capacity of 1 gram of water is 4.18 joules per degree C? So we know the capacity then would be 4.18 over 1 gram, which would then give us the specific heat of water as 4.18 joules per gram degree C. So heat capacity then is independent of the amount of the substance. So it doesn't matter how much of the substance we have, right? The specific heat of silver is 0.235 joules per gram degree C. What is the heat capacity of 100 gram sample of silver? So of course here you can multiply through by the 100 grams and it tells us it's going to be C, 23.5 joules per degree C. So again, capacity would equal specific heat times mass. You can take that specific heat times the mass, plug those in, and that gives us the 23.5. Here we can see the grams cancel out, and we're left with joules over degree C. All right, so some specific heats for different substances. So carbon, graphite, 0.711. Compare this to water. So first thing I always look at is we're in joules, right? So in joules, we know that water is going to be 4.184. That gives you kind of an idea of how much heat is being released or being absorbed by a material. So you can see graphite here then at 0.71, ethyl alcohol is close to water. Metals typically very small, 0.129, iron 0.44, lead 0.128. So obviously silver 0.235. So obviously they, allow heat to pretty much go through in large quantities, right? All right, so using specific heat then, heat will be exchanged. That means that specific heat times mass times a delta T. So Q is heat. It's equal to now specific heat times mass times delta T. Now remember, that's the same as the capacity, right? So specific heat and mass together. So these equations are very much like what we saw, except now we're going to be able to break down the specific heat and the mass. The units here, right, you'll have joules per gram degree C times joule times degree C, which means it's going to equal joule. And substances with high specific heats resist change in temperature when heat is applied. So water has unusually high specific heat. All right, now this is very important. It's important to the body because you are 60% water. Okay, it's used to cushion temperature changes. So why coastal temperatures are different from inland temperatures, right, is because of the heat capacity of water. Calculate the specific heat of a metal if it takes 235 joules to raise the temperature of a 32.91 gram sample by 2.53 degrees C. All right, so we'll start with our basic equation here. Q is equal to M times S times delta T. And let's see what we have here. What we're looking for, calculate the specific heat. So we're going to be looking for S, which means the first thing we can do is rearrange then. So we know that S is going to be equal to Q over M times delta T. Now what we're going to do is plug and chug. They told us our heat is 235 joules. Our mass is going to be 32.91 grams. And of course our delta T, because they want the whole change, if we're going to raise it by the temperature of 2.53. So that is our delta T. And at that point we plug and chug, and that gives us 2.82 joules per gram degree C. All right. So the specific heat of copper metal is 0.385 joules per gram degree C. How many joules of heat are necessary to raise the temperature of a 1.42 kilogram block of copper from 25 to 88.5 degrees C? Now, just like in the question here, they've provided the specific heat. I don't expect you all to memorize specific heats. I will provide those for you. So they'll either be in the question like this, or sometimes I'll actually just pull it out and say the specific heat of this is this. Or the question will actually be asking you to solve the specific heat like we just saw in the previous problem. So keep that in mind. You don't need to memorize any of those numbers, right? All right, so as you work through this problem then, here are your potential answers, and you can pause here if you want, and then do some work, and then hit play. And after you hit play, hopefully you've come up with 3.47 times 10 to the 4 joules. All right, so we're going to start with our basic equation. Q is equal to M times S times delta T. Right? We know delta T. This time we'll have to calculate it because it's not just handed to us. We know we're going to start what? From 25 to 88. So 88 will be our final temperature. 25 will be our initial temperature. So we'll subtract those two. That'll give us delta T. Now, a lot of times in lower levels, I tell them don't worry about sign, but you all do need to worry about sign because later we're going to see where I need you to be able to tell me if something is absorbing heat or if it's getting rid of heat. So is it allowing heat to go out or is it pulling heat in? That's all the difference in the sign and that temperature change right there. So had it been the other way, if we were letting this thing cool, then it's releasing the heat, and we would see that as a negative value at the end. So you do want to keep track of that, pay close attention to it, because that's a lot of the times where students will kind of slip up a bit there. All right, so now that we have delta T, we can plug that in. So Q is equal to M times S times delta T. We're looking for Q because it says how many joules of heat. So that means we have the mass. We're told it's 1.42 kilograms, right? We're probably going to want to convert that to grams first. Then once we have grams, we have delta T. We need the specific heat, which they gave us in joules per gram, so we should be good. We should have everything we need now. So it's going to be 1,420 grams times the 0.385 times that delta T 63.5. Here we can see the grams will cancel out. We can see degrees C will cancel out, and we'll be left with joules. We run that through our calculator, and we get 3.47 times 10 to the 4th. All right, so as I just was mentioning, direction of heat flow. So heat is the energy transferred between two objects. Okay, so heat lost by one object has the same magnitude as heat gained by the other object. Now, in our course, we're going to assume perfect systems here, so it means all the heat that's lost by one object is going to be completely absorbed by the other object. And most of our real world ideas here, that's obviously not going to be true, right? Because the heat is going to flow into a lot of different places, and it's not all going to be just from one object to the next. Okay, sometimes it's going to go into several different places. All right, so your sign of Q then is going to indicate your pressure or your direction of your heat flow. So heat gained, Q is going to be positive, and heat lost, Q is going to be negative. Okay, so Q1 would equal negative Q2 in any normal transfer that we're going to be looking at. A piece of warm iron is placed into a beaker of cool water. Iron loses 10.0 joules of heat. That means the water has to have gained 10.0 joules of heat. So Q for the iron then would be negative 10, and Q for the water would be equal to positive 10. If you've ever taken an accounting class, this is very much the same idea, right? If money goes from one account to another account, it's got to be a complete transfer, and you show that. This one is the one that gave the money. This is the one that took the money. Okay. A cast iron skillet is moved from a hot oven to a sink full of water. Which of the following is false? So we have a cast iron skillet moved from a hot oven to a sink full of water. The water heats. That would be true, right? Because we're assuming the water was probably around room temperature and we put the hot skillet in there, the water has to get warmer. The skillet cools. Yeah, that one has to be true as well, right? Because if the skillet is hot and we put it in cooler water, then the temperature has to balance out. The heat transfer for the skillet has a negative sign. Is that true? So yeah, the skillet's losing its heat to the water, so that's going to be a negative sign. The heat transfer for the skillet has the same sign as the heat transfer for the water. Okay, that's definitely the false one, right? Because we just said if one loses, the other has to gain, and we're going to show that difference with a positive or a negative sign. All right, so using heat capacity then, a ball bearing at 260 degrees C is dropped into a cup containing 250 grams of water. The water warms from 25 to 37.3. What is the heat capacity of the ball bearing in joules per degree C? And the heat capacity of the cup of water is going to be equal to 1046 joules per degree C. Okay, so now looking at this idea of sign, we know that the Q lost by the ball bearing is going to be equal to the Q gained by water. So the first thing we're going to do is determine the temperature change of the water. The temperature change of the water is going to be 37.3 is where it ended, but it started at 25. So that's going to be a positive 12.3 degrees C. Next, we're going to determine how much heat was gained by the water. So we were told the capacity was 1046. We know the temperature change. So Q for the water would be equal to capacity times temperature change. So 1046 times the 12.3. That gives us 12.87 times 10 to the third joules. Okay, so there's our heat. Next, we want to look at, determine how much heat the ball bearing lost. Well, we know that the Q of the ball bearing would equal to the negative Q of the water. So that means negative 12.87 times 10 to the 3 joules, right? Now we want to determine the temperature change of the ball bearing. Delta T for the ball bearing. It also ends at 37.3 degrees C, but it started at 260 degrees C. That's going to give us negative 222.7 degrees C. And now we can calculate the capacity of the ball bearing. We know the heat is negative 12.87 times 10 to the 3, and we know the temperature change was negative 222.7. Negatives will cancel out, and of course we'll end up with 57.8 joules per degree C. All right, hopefully all that made sense. You might have to go through that a couple times. All right, now let's try it with specific heat. So how much heat energy must you lose from a 250 milliliter cup of coffee for the temperature to fall from 65 to 37? Assume the density of coffee is 1 gram per milliliter. Right? We're going to assume that the specific heat of coffee is the same as water, which is 4.18 joules per gram degree C. Our base equation is going to be Q is equal to S times M times delta T. So we're going to look at how much heat energy must be lost. So we're going to be looking for Q from a 250 milliliter cup of coffee. And what's that going to give us? Well, that's going to give us our mass, right? Because we have 250 milliliters, and we're told down here that we're going to assume the density is 1 gram per milliliter, times delta T. And here we're going to go from 65 to 37. So it's going to be 37 minus 65, right? So delta T will be 37 minus the 65. That's going to give us negative 28. Now we can plug into Q. We're going to assume that the heat capacity, or the specific heat for the coffee, is the same as water. So we're going to put in 4.18 joules per gram degree C. We're going to assume that's 250 grams. So it's going to be 250 milliliters times 1 gram per milliliter. That way our milliliters will cancel out. We'll have grams times our delta T, which is going to be the negative 28. Grams here will cancel out. Degrees C will cancel out. Our answer then will be in joules. And it works out to be negative 29.3 times 10 to the third joules. Now what's that mean? Well, that means that Q is equal to negative 29.3 kilojoules. And that should make sense. The coffee is cooling down, and so it's going to be releasing 29.3 kilojoules of heat. All right, third example here. If a 38.6 gram piece of gold absorbs 297 joules of heat, what will the final temperature of the gold be if the initial temperature is 24.5 degrees C? The specific heat of gold is 0.129 joules per gram degree C. So you can see it's a pretty common technique to give you the specific heat of the metal or whatever it is you're looking for at the very end. So again, you don't need to memorize those numbers. You'll see if you can find them. You can either look them up or they'll be provided somewhere in the question. All right, so back to the question though, what will the final temperature of the gold be if the initial temperature is this? So basically we're going to be looking for delta T, right? So we need to find T final. So we know delta T is equal to T final minus T initial. So we're going to use our base equation then simply to calculate delta T and then plug it in and figure out what T final is going to be. So delta T is equal to Q divided by specific heat times mass. Let's see, they gave us the Q, right? They told us how much heat was absorbed. We know the specific heat of the metal, they told us that at the end, and we know the mass. So it's going to be plug and chug to get that delta T. Got 297 over the 0.129 times 38.6. We can see joules cancel out, grams cancel out. That's going to give us 59.6 degrees C. Now remember, that's delta T, but we need to calculate T final. So we're going to plug and chug, right? 59.6 degrees C is going to be my delta T. That's going to equal T final minus the 24.5, which means I'm going to add 24.5 to both sides, which gives us a final answer, excuse me, of 84.1 degrees C. All right, so I've given you a few examples here, and now of course it's going to be your turn. So what is the heat capacity of a container if 100 grams of water at 100 degrees C are added to 100 grams of water at 25 degrees C in the container and the final temperature is 61 degrees C? All right, so hopefully you paused and pushed play again and you came up with 35 joules per degree C. All right, so here's the solution. We know that the Q lost by the hot water is going to equal the mass of that hot water times delta T times the specific heat of water. So we can plug all that in, right? Because we have the 100 grams. We know we're going to end at 61. We're going to start at 100. We know the specific heat of the water is 4.18. And so that's going to give us negative 1.63 times 10 to the 4th joules. Right? Make all that stuff cancel out. So we're in joules. That means we know that the cold water gained, right, 100 grams. We're going to go to 61 again. Cancel that stuff out. 1.50 times 10 to the 4th joules. Okay. So Q lost by the system then would be 1.50 times 10 to the 4th joules plus the negative 1.63 times 10 to the 4th joules, which gives us negative 1.3 times 10 to the 3rd joules. Okay, so we figured out the heat that was lost by the hot water, the heat that was gained by the cold water, and now the difference between the two. Okay. So Q container is going to equal the negative Q lost by the system. So that means we have 1.3 times 10 to the 3rd joules is what the heat was for the container. Okay, so the capacity then would be the Q, the 1.3, right, divided by the temperature change, gives us 36 joules per degree C. All right, and I think we're going to end this segment here because next we're going to look at how the chemical bonds are going to be playing their part in all of this energy. Okay, so that'll be the focus of segment 4, and so we'll talk to you soon.